So I really enjoy doing these unscripted videos. They're actually a whole lot more fun than, hey buddy, than the tightly scripted I forget to say words and I add extra bits videos. Much, much harder. Hop up. And from the last one, we touched on magnetic tech lightly. So I wanted to go into high energy pulsed electromagnets. And for those that aren't super keen on electromagnetic design, I suggest you switch to the next video. I will go through a bit of detail here and it will jump occasionally, but again, all the elements are out there for those who are interested and willing to go and do some research. Now, I mentioned in the last video, niobium tin and niobium titanium were the kind of two core magnetic materials that we use. Now, these are set in copper wires with thousands of filaments, and they're tiny, which is great. And this starts to affect your magnetic performance. Now, one of the really interesting goals, because I mentioned last time that we haven't really come up with anything cool since the 60s in terms of magnetic material that can make a functional and practical magnet. Hey Ben, you want to come here? I'm just going to put these here. And that's a bit of a limitation. You know, we are another 60 odd years down the track from the 60s now. And if you can't improve the material, what can you do? You can improve the design, you can improve mechanical stability, all sorts of things, but you still come to these hard limits. So there are certain points of optimization where you are then forced to go and look into other areas. Now, high energy pulsed electromagnetics is focused on achieving 100T fields. And this has been done at quite a few facilities around the world, like Dresden High Magnetic Field Center, the Wuhan National High Magnetic Field Laboratory, and CERN. They've been onto it for quite a while. So if you want to read up on magnet tech, I suggest Rusenschak 2010. He's got Field Computations of Electromagnetics, and it's actually a great read. I really never thought I could be excited about a textbook, but that was a good one. My other friend, Oasa, Case Studies in Superconducting Magnets, is also a pretty good time. And then you'll see on my Instagram, there is like one set of pages from quite deep in the book that shows you that superconductive electromagnetics can be solved with multiplication in an Excel sheet to a degree. And again, like the last video, there are numerous concerns of reality that need to get built into that. But as a first pass method, before you start really delving into MATLAB and numerical modeling, it's a pretty good start. So, we can't improve the materials. We need to turn the magnets on and off quickly, and we've got the goal of getting to 100T. Now, particle beams are all quite different, funnily enough. And you can end up with long consistent streams, you can be shooting for like point targets, but at the end of the day, you still need to pulse your magnets for a certain amount of time to make sure that the crux of the beam gets around the bend. Now, once you're hitting 100T fields, awesome, but high power. So your pulse duration's not as long. So you start to have to consider this equivalence between, well, how strong a magnet do I really need? And from there, based on the available power supply, how long can I pulse it? And eventually you're going to come to an optimal point based on your use case. So for us, we have focused on building a satellite mounted high energy pulsed electromagnet. Now, it's again a simple solenoid. I talked a little bit about yoke construction in the last one. For particle accelerators, the yoke sits around the outside of the coil. Again, it's just a focusing element, and especially in tunnel-sized electromagnets, it's also good for cooling, which is known as the cold mass. Again, I'll cover refrigeration in another video because that is a whole topic in and of itself. But suffice to say, liquid helium is pretty cool, especially below 2.7K. Now, if you can have superconductors running with very little, virtually zero resistance, they need to be quite cold. We've got high temperature superconductors, we've got BISCO 2223, and these are great for putting the leads into the magnets. But the core of it is still what we mentioned. NBSN3 in a copper matrix. Now, niobium titanium is, by all considerations, cheap to make and use. It's reliable, but it caps out at about 4T field, as where niobium tin caps out at about 25T. So there's an appreciable difference in the quality. But this comes with mechanical stress considerations. You know, do you need collaring at the bottom of the coil to actually support it? Because the top and bottom of the coil, where the power goes in and out, are at a tangent to the direction of the magnetic force, and this can end badly for your support structure. And when you're designing it, you're shooting for a use case. So you know your requirement. You're going to have an element for safety. Say you want to use 60% of the magnetic strength. And there are numerous ways we can quench train to get things a little better. But again, I'll return to quench training in a tick. So we've got a magnet. You can fit it in a space, and you can use the remaining space for available power. Again, returning to that optimal point, you should be able to work out this actually fits inside a satellite really comfortably, worryingly easily, and I don't know why anyone hasn't come up with that before. But solenoids aren't new. They are certainly not new in satellites. And, well, anyone that's ever owned an iPhone in a cold country will probably tell you the battery isn't as good. And so the one major problem is our energy storage method. Now, lithium ion is pretty prevalent. It's pretty cheap, and the energy density is pretty good. So, you know, you've got this magnet that can survive thousands of life cycles, and you've got a power system. Again, I'm assuming you have optimized these so you're not taking a giant magnet and like too few batteries, because that's not overly clever. But, well, coming back to that cold country problem, the batteries aren't any good if they lose all the charge and they can't hold as much as they need. And you'll start hitting that safety threshold really quickly if your batteries have degraded to 60% of what's required. Now, in battery technology, we've had, again, incremental improvements over many years, but we haven't had any transformationally new technology in a while. I was reading about a new partnership Tesla are investigating in a new battery tech in the last month. Awesome, but still waiting to see. And I know my design works with lithium ions. You got to keep them near room temperature. That's quite painful in space, but electromagnets put out a bit of heat, so the issues of one become the solution to another. Yeah. Again, considerations, reality, numerical modeling, go and prove it with an electrical diagram, a heat diagram, and then make sure this all interacts properly in your very challenging to lose heat environment. If you cook your satellite, it's not going to work. If you cook your electromagnet, it's not going to work. And that's where quenching comes in. So quenching is a loss of superconductivity in a rapid change to a normal resistive conductivity. And if you have a whole lot of energy expelled from your superconductive filaments into that copper matrix all at once, you're going to crack a coil. And while awesome to do experimentally, not so cool in space. Very, very hard to fix. And that's why I focused on making a mass-producible and cheap-to-use design. Ideally, you want to have these satellites coming off a production line and ready to roll in any environment. Drone swarming tech, as I alluded to last time, allows setup. So we've got we've got a power problem, but it can theoretically be done cheaply. Well, what if some of the technology we were looking at was like eutectic mixtures. You can start to use some really interesting cold temperature capacitor chemistry by blending fluids together and storing charge in them. Now, this is still experimental tech, or at least it was several years ago, and I like to think they've probably operationalized it a little bit further, but I've yet to go reading. Mostly, I did my proof on NBSN3 and lithium ions, and anything better only makes it easier. So, just returning to the eutectic mixture for a second, a lot of lithium is rated for about positive 10 to about 50 centigrade. And while lower atmosphere, or low Earth orbit could be considered relatively near room temperature, provided you're in the right, with the right degree of solar radiation, as you start to get further out towards that edge of space in high Earth orbit, it gets a lot colder. So, again, unscripted video, forgive me if I get this in the wrong order, but it's BMIBF4? It's like a borofluorate, tetraborofluorate. Anyway, so a couple of these combined work really well at minus 50. And cost benefit, providing they're not too bad to get a hold of. One thing I love about research papers is they often tell you who made them and part numbers. Incredible as an engineer and a designer. So I started to work on a multi-coil solenoid design. Now, pulsed electromagnets, circling back, got to this point where they said, our goal is 100 T fields, we want a longer pulse, so, well, building really big coils is not the answer here. Let's go multiple smaller coils. You fire the outside and you move sequentially in. And now each inner core pulses for a shorter amount of time and must hold the subsequent field, must hold the combined field of the other two. And then you get this little pulse. And that's how you get to 100 T. But if you're only doing it for fractions of a second, is that a problem or is that a benefit? One thing I'm really excited about as an old mining engineer, drill and blast is awesome. I wrote my undergrad thesis on it, and blasting mechanics, incredible. But again, commercialized software, this isn't new stuff. If a mine blast is going to remove as much risk as possible, you start to look at some pretty precision timing. And again, wave interaction, interference, all sorts of considerations, reality aside. Now you're considering instantaneous delta V maneuvers in space, and you know that there's very little air resistivity. Or none, because it's a vacuum. Which is why heat's hard to lose. But also there's no friction. So our magnet uses several coils with sequential energization from a cold temperature capacitor chemistry. And as I roughly alluded to last time, if you're shooting for a 0.5 meganewton target and you're able to solve this as an iterative layer problem, and you're shooting for 0.5 meganewton divided by 4 satellites, it all starts to look pretty good. Now, these pulsed electromagnets are, as mentioned in some of these other facilities, are test cases. Industrially, you can go and hire time on them, just like old timeshare computers. So you can go and test designs, you can go and test configurations, and research grade coils like that, they're designed to be used thousands of times over and over and over. Now, if you take that as a starting point, you just take all the same cabling, stick it in the right size configuration, optimize to your point of power storage, how far do you think we can get? Or how big a cargo do you think we could move? You know, if we are shooting for that instantaneous delta V, do you want to try and hit a bowling ball with a whole bunch of tennis balls and yeet them off into the atmosphere in the opposite direction? No, probably not. That bowling ball is going to stay where it is. You want that bowling ball off and on its way down the lane. So, what if you could electromagnetically tether all of these tennis balls together, and their combined mass, along with the offset of thrusters and, again, a few other considerations of reality and timing, this is where our difference is. And I do not know why no one's come up with it before.